So, good. Essential crew member is here. So now we can start. Today, we shall talk about, finally, the tangent groupoid. That day has come. Every October or whatever it is, from now on, 5th will be tangent groupoid day. Okay. But just to be gentle on the analysts, we'll just talk about Rn today. No, one step at a time. So I'm going to define the tangent groupoid in a way which is, not the most functorial, or maybe, and certainly not the most general, but it's by far the closest to what we've been doing up to this point. So that seems like a reasonable thing to do. And then next week will be a little more, I don't know, geometric, and we'll redefine this whole thing in a way that Dan would like. Okay. So eventually we'll talk about general manifolds, but today that's not the case. I want to imagine a situation in which we have a smooth manifold. It'll happen to be, okay, so the word manifold did appear in this class, but in the main example, really the only example we'll study today, W will be Rn plus 1, n plus 1. So yeah, don't panic if you're an analyst, it's still Rn plus 1. And I want to consider this situation to begin with, in which there's a Lie group, which is acting on the manifold. So there's here a smooth group action. And if you don't like Lie groups, don't panic. The group here will just be the group Rn, the additive abelian group Rn, acting on Rn plus 1 in a slightly funky way, but only very slightly funky way. But suppose we have this situation here. Everyone can think of dozens of examples of such a thing. And whenever you have such a thing, you can build the following space. What am I calling it? W. And I'm going to make it out of triples like this. So, of course, the W's come from W and the G's come from G. And what this is going to be, if you like, it's going to be the graph of this. This is a function, so it's going to be the graph of this function. Yes. No, thank you very much. W1, yeah, thank you. So there are two different W's and a G, but there's a relation between them, which is that W2 is G of W1, like that. So you don't have to say what is W2, because there's a formula for it in terms of G and W1, but it's nicer to write things down in this way. And this defines a certain space, which, like I say, you can think of as the graph of this smooth map, which is the group action. So it's a smooth manifold, a smooth like any graph, it's a smooth submanifold of the domain times the range, and it's actually the same as the domain just by projecting down, just like take the graph of y equals x cubed. Well, if you're a manifold person, that's just R, right? That's just the line. just project down onto the line, and that's a diffeomorphism. Same thing here. This is not a complicated manifold. Let's call it G, and then what's that she's doing there? Let's get rid of that one. And then this L times symbol from LaTeX, like that. Semi-direct product, something like that. Okay, so this thing is what's called the transformation groupoid. Associated to the above action. Yeah. And we'll get slightly more serious about groupoids in a moment, but maybe we should just say just one little thing to get started. What about this horrible word groupoid? This was a colossal blunder that happened, I don't know when, that someone took the word group. I don't know who's responsible for this and put oid at the end. It's like deviant. It's like a deviant group, or I don't know what. It's a terrible terminology. You're kind of used to it now. I mean, Eckhart's looking at me and saying, what's wrong with it? Well, that's because, you know, you're used to it now, but it's deviant and wrong-headed to call something oid like that. But it's too late. Elliptic operator is not, okay, it's defendable. Hypoelliptic, okay, if you're a Greek scholar, it's still defend. I mean, there are lots of things in mathematics which are not defensible at all. Parabolic induction, I mean, come on, there's no parabola in sight anywhere. Okay. Oid, okay, it's oid. What does oid mean in this context? It means it's a deviant group, right? It's like a group, except it's defective in some ways. Yeah, but they, you know, it needs to be. If something has flaws like that, you have to. It's a matter of marketing. You have to market the thing in the right way to get people to like it. And just saying, sorry, this group is deviant. It's, you know, defective. I don't know, but you know, something a little more positive. Anyway. Hypo, yeah, something kind of hypo group. I don't know, less than group.
Because there are also pseudo.
And also that's that's also terrible. But it has to be something completely different. I think that's the answer. You just jump into a different terminological realm. That's the way to solve this problem. But it's too late. That would have been the way to solve this problem. Too late now. Okay, why is it? What's group-ish about this, oid-ish about this? Well, if you have one triple which satisfies this law, namely the graph law, which is over there, and another one which also does it, you can sort of multiply them together according to a really simple formula, which would be simple if I got the numbers right. So if you have two triples, these aren't completely arbitrary triples, because after I got the typos corrected, I made the second W in the second left-hand triple equal to the first W in the right-hand triple. And now what you can do is, it's really nice. You can just write down W3, G2, G1, W1. They sort of multiply in the world's nicest possible way. Can't argue with that. And so there's some sort of algebraical structure, which we'll get back to in, on, around, in this thing. That's why it's called a groupoid. So, you know, you can axiomatize what this is, and in due course, we will axiomatize it. Okay, but that's not what we want to do first, because what I'm trying to do is make you demand that I tell you what the axioms are by showing you just how beautifully suited this is to our problem, which is to understand pseudo-differential operators, our current problem. So we'll get back to this algebraical multiplication law, which is a little deviant because you can't multiply arbitrary two elements. There has to be a matching condition in the middle for the multiplication to make sense. That's the, that's the hidden disability of this object, why it's only an oid. But most important for us, at least for today, is a certain map. There are actually two maps, and they're equally important, but it's helpful just to choose one over the other. So the one that I'm going to choose as being the most important, I'll call source, and what it does is it sends one of these triples that we've just been talking about W2, where you're supposed to read these things from right to left, so that's where it begins. Sorry about that. The W1, which is now where it begins. But if you wanted to, if you were, left-handed or something, you could do it the other way around. And send such a triple. Let me try to write it correctly. For the other fellow, W2. And what we want to do today is think of this entire space as a sort of bundle of objects that we'll call source fibers. So we'll just pick a little w in W and only look at those alphas which begin at that W. So the fibers are parameterized by points of W. So once you've fixed W, let's just go back to these formulas here. Once you've fixed W1 by fiat, as I have in this construction here, what are the possibilities for W2 and G? Well, G can be anything, but then W2 is prescribed to be G times W1. So if you pick a source fiber, if you take a source fiber and you write, instead of writing it in the elements in this source fiber obscurely as alpha, if you wrote them as W2, G, W1, then the projection map, which just picks out the G, is a diffeomorphism from this source fiber to G. So in this particular case, which is the case we'll be focusing on today, these things are all diffeomorphic to G by, how to say, projection. So that's how things look in this particular group oid, this particular deviant group. So that just happens to be the way it looks here. There are other groupoids that you can also think of as collections of fibers, source fibers, and then the source fibers don't always have to be all the same like they are in this space. And but in this particular situation, this is what the fibers are. Okay, so I'm just, so far, a groupoid is, for us, most importantly, a collection of manifolds all glued together in a nice, smooth way. Collection of submanifolds all glued together in a nice, smooth way. Okay, that's just one way of looking at these groupoids, and probably one of the ways that Eckhart and Dan are least fond of. But because we're doing analysis and operator theory, it's convenient to have all of these manifolds, because we can imagine a situation in which we have an operator acting on the functions on each of these manifolds, one operator for each source fiber. And now we have a family of operators, and we've been speaking for the entire semester about families of operators, scaling families and symbol families, and I don't know what families. And so that's going to be the connection to what we were just discussing. We've been discussing families of operators of this kind or another, and all of those operators act on functions on spaces, and now we're making an effort to take those spaces and glue them together in an intelligent way. And you'll see why in due course. Yeah.
I know that there are always families of operators like theorem. This like one way of particularly nice.
Yeah. So, I mean, we shall be studying families of operators the rest of this lecture, at least, ad nauseum. And yeah, this produces a very nice picture of what they are. And then we'll come back to this picture in due course, and we'll make it even nicer after we've built the so-called groupoid convolution algebra. Yeah, I mean, groupoids, as you know, do many things. This is just one narrow perspective vista along which we can look at groupoids, but it's the best for what we're doing right now.
Like, it's sort of, I guess, like, I'm just thinking of this perspective, like, oftentimes you think like X times Y or something, you know, family operators on X for X times X times Y, but the space is kind of trivial. So like in this case, you don't have like an actual product, and it's not even locally a product, but you still have ways of going from one fiber to the next.
Yeah. I mean, let's just, as a parenthetical remark, let's just imagine another example. Probably shouldn't do this. It's probably going to be more confusing than helpful. Let me see if I can get the notation right. Suppose you have a submersion from one manifold to another. Maybe a surjective submersion. That means the derivative has derivative of a map between of several variables as a matrix, and this derivative should have maximal rank as a matrix everywhere at each point. Okay, then you can build the following thing. Namely, you can just take pairs of points with the property that they project to the same point in the base, like that. And these guys also have the same sort of multiplication, which we haven't yet formalized, but there's some sort of multiplication allowed on these things here. And now, suppose you're following the works of Attir and Singer, and you wanted to study index theory, not for a single operator, but index theory for a family of operators. Well, for example, you might have some differential operator on the big space Z, which only differentiates in the fiber direction. So in other words, the differential operator commutes with multiplication by functions on the base, W here. So that breaks up into a whole bunch of operators, one on each fiber. And then maybe you might want to find a whole family of parametrices of those operators, a whole bunch of Qs to go along with the Ds. And then you might want to study 1 minus dq and 1 minus qd, and those are going to be families of smoothing operators. And you can see that the integral kernel of such a family of smoothing operators is going to be a function on this space G. And so it's rather nice how it works. And after I've mentioned integral operators, you can look at this formula here in a new light, because it's sort of reminiscent of matrix multiplication. If you have a little matrix unit EIJ, and you multiply it against another little matrix unit, EJK, then what you get is EIK, kind of like what you see here. So lurking in the background is some idea that of matrices and smoothing operators, and that, of course, is the direction in which we're initially going to be going. Did you have? No. I was wondering if you had a question. You were just no. Okay, good. All right, but that's. I just mentioned that in response to Dan. So far, so good. Wow, you just look like you're just on the edge of about to ask something, but not so, not so. Okay, so let's now. I think yeah, let's do the following thing. So. Rather than looking at general examples which don't quite necessarily fit into this context here, let's look at a particular example of this construction. There are going to be RNs all over the place. And I think it's helpful, maybe I'm wrong, but I think it's helpful to use different letters for the different guises that this Rn has. So if I write A, it means Rn, but I'm thinking of it as an abelian group, something that acts on something else, like on the board to my right. What about the manifold? Well, in this particular case, the manifold is going to be a product of M with R. And what is M? Well, that's just another copy of Rn, like that. Okay. And now I need an action in order to perform this construction of A on W. And here's what it's going to be. So I'll write a point in this product space using coordinates. M means a point in Rn, and T means a number. And I'm going to, because it's an abelian group, I'm going to write the action with a plus instead of a dot, you know. And what this is just the scaled version of the usual addition action, like that. And as for T, it's the T coordinate's not getting stirred around at all. The action is all the action is taking place in the M coordinate. Okay, but that's a group action. If you like, it's a family of group actions, smooth family of group actions parameterized by R, or you can just think of it as one action. All right. So now there's an object that we can build somewhere, maybe up here, which is this object. So if you like, what does it consist of? It consists of pairs M2, T2. I'm just doing this once, and then we'll agree on some simplifying convention after this. And so what's the condition? The condition is exactly wherever it was, this condition up here, which means that, well, nothing is happening in the T variable. The T's have to be the same. And as for the M's, let's just call that T. As for the M's, M2 has to be TA added to M1. But it's going to drive us crazy to be writing T1 and T2 all the time. So let's just tidy up the notation a little bit. How about this? let's officially define this space in the following way. So here is exactly what a semi-direct product W will be. And now I'm just going to define a version of it, which I will officially call TM rather than a semi-direct product W. And I'm just going to tidy up the T's a little bit. There's no point in writing T1 and T2. I mean, already this notation is redundant, but it would be even more redundant to have T1 and T2. And there are limits to, even for me, there are limits about how redundant I want to be. Okay, so now the condition is that M2 is T, A plus M1. So this will be our, for today at least, the exactly what the tangent groupoid is. We're taking advantage today of the fact that the particular manifold that we're studying, just Rn, it admits a free transitive action of a group. It is a group. And when we define TM for something which isn't so nice, then we'll have to use some different terminology. In fact, it admits a free and transitive action of Rn. That's important too. Okay, so we built this thing, and it comes from this action here. And it seems like this action is all about everything that a vector space is about. Look, there's scalar multiplication and there's addition, and that's it for vector spaces, right? It seems that we're fully invoking the vector space structure of Rn in order to make this definition. I guess we are, if we're making it the way we're going to make it, but something interesting is going to happen in that regard. And as before, the most important thing for us, like we see here, is going to be the source and range maps are going to be, but we'll focus on the source. I mean, there is this sort of multiplication, if you like, which would look like this. See if I get the, anxious to get the numbers right here. That would be this strange deviant group multiplication that we haven't really dwelt upon yet. Okay, but most important is this source map and its friend, the range map. So this goes down to W, and W is M times R. And what happens? Of course, it's just this, M2A, M1T. Just goes to M1T. And there's another similar map, which is the range, and the image of the range is M2T instead of M1T. Okay, so this space is T of M, which is a manifold. Of course, it's just R2n plus 1, because it's A times R, N times R. This space is decomposed into a bunch of fibers, and we happen to know that all of the fibers look like A, but we'll do something a little different. We'll think of them in a different way, but they all are just copies of A. So you're supposed to be thinking of this thing as a ginormous bundle of manifolds, collection of copies of manifolds. And the indexing set, the parameter set for this collection of copies of manifolds is Rn times R. And if we temporarily call the members of Rn, the elements of Rn, omega, and if we temporarily call the element, well, if we call the elements of R just numbers T, then there's a manifold for each pair omega T, just like in former times, meaning on Tuesday, there was an operator for each pair omega comma T. So there are as many fibers in this construction as there were operators in our theory of scalable operators. That's not supposed to be a coincidence. All right, going super slowly through this. I mean, why not? Yeah, so let's write these source fibers. Like this. So I'll call them M sub something. And this will just be the set of all, I don't know, M prime A M T's, obviously satisfying the correct relation, which is that. And now something a little bit interesting happens. I call these in these notes. Yeah. Well, okay, fine. I don't know whether to put parentheses around this or not. Probably will not be consistent. What are these spaces? Well, if T is, of course, we know all of the source fibers look like A, but if T is not 0, they also look like M, because you can take a quadruple, I guess it is, M prime A M T, and just send it to M prime, and that's a diffeomorphism. Because if T is not 0 in the equation which defines membership in the source fiber, you can solve for A. A is actually a function of M prime, isn't it? So once you know M prime, you can figure out what A is by dividing by T, which is legal if T is not 0. And so this projection map here is a diffeomorphism.
Excuse me, I had a question. The question, I mean, it might be a little silly, but when you are looking at the tangent space of the manifold and writing M2 is equal to TA plus M1, so does it in any way represent a straight line which corresponds to a tangent and something like that?
Yeah, tangent vectors are definitely in the picture here. Maybe I'll write this down somewhere. Here's the definition of the tangent groupoid. Just do a little bit of arithmetic. Of course, from the equation which characterizes what is the tangent groupoid, you can solve for A as long as is not 0, like that. And so that makes A look like a little vector pointing from M1 towards M2 with length 1 over, well, with length of this thing, this quotient. So that looks like a sort of, the sort of thing, a little, what's it called, difference quotient that you see in the definition of the derivative. I mean, if I had a function on this space, then I could take, on the manifold M, I could take f of M1 minus, f of M2 minus f of M1 divided by T. And as T went to 0, that somehow would be like a derivative, wouldn't it? So there are tangent vectors lurking, and we'll make that explicit in due course.
Thank you.
You're welcome. Now, where was I? Oh yeah, we just defined this thing. What about, what happens when T is equal to 0? Well, you can't do what I just did when T is equal to 0. But you can do what you can always do, which is identify the source fibers when T is equal to 0 with the group A, because you can always do that all the time. I guess I could still call them phi. There would be no overuse of notation. But the best you can do when T is equal to 0 is now what do we have when M is equal to 0? Let's look at our basic equation here. Suppose we have an element of the tangent groupoid, an M2 and an M1 and a T and an A and so on, just like you see here. But T is equal to 0. If T is equal to 0, then M2 is equal to M1. That just follows. So the only thing that's in this is a single M and an A. Everything in the source fibers at 0 look like that. And the best you can do is to send this to A. So there are two different ways of thinking of the source fibers depending on whether T is equal to 0 or not. Yes?
Presentation of the source fiber, don't you write TM? Just M.
Oh, you're complaining about the notation. Yeah. Yeah, this notation, the reason I'm calling the source fibers this is I want you to think it's basically M, which it is in these cases. So the notation is designed to suggest what the thing is rather than conform to some general principles. Yeah, a groupoid is usually called big G, and then these, which we're using TM for the groupoid name, and then these source fibers are called something like big G sub gamma. Not gamma, big G sub X, or X is a so-called object, an element in the range space of the source map. So the notation is tailored to our particular purposes. It doesn't fit general notation. Okay. No further rationalization will be given. Okay, good. Maybe it's time to let the cat out of the bag. Yeah, let's do some stuff with differential operators. Oh, definitely. Let me just write down a formula for a differential operator on Rn. Can't call the order M anymore. I hadn't anticipated this issue. M is a point of big M. So the order now will be R, to go back and change all the little M's into little R's. Maybe I'll just globally change in the file all of the M's to R's, see what happens. Okay, same thing as before. Okay. I don't think the word. Yeah. I don't think the word mange appears anywhere in the notes, so that's one possible source of confusion that is eliminated. Anyway, here's an operator D. Let's do something because it seemed like such a good idea. Let's do it again. Let's just multiply D by the order like that. Based on just how much fun we had doing this in the previous weeks, let's just do it again. dt is t to the r times d. Okay, it would be kind of dumb to do this when t is equal to 0, so let's not do that. Okay. And now I want, so this is an operator on Rn, M. And now we have a whole bunch of manifolds here, these M sub mt's, especially when t is not equal to 0. We're in this situation that I'm writing down here, which are basically M. So what I'm going to do is just repeat the formula that I've written down there on each of these manifolds, M sub mt. It's going to be the same operator, just repeated again and again and again, just using this stupid identification, which, yeah, I got the prime right. So let's define. I wish I'd given myself more room. I guess I should do it over there. Sorry about that. Well, I'll squeeze it in here. I'm going to build an operator on each source fiber, at least when t is not 0, to begin with, in the obvious way. Here are the functions on M sub mt. I want to build an operator on that space of functions. That's what a differential operator is, excuse me. So the operator will live here. Maybe I should say will act here. But of course, this space is just a copy of M, of C infinity of M, just by composing with phi mt. So this map here is phi mt composing with. I'll put a little star to indicate composing with. And the thing downstairs will just be the thing I call dt. So nothing happened. No, you can see my hands, nothing up my sleeves. It's just nothing happened. Okay, did the world's simplest thing. Something did happen. We have lots and lots of operators now, one for each m and one for each t, as long as t is not equal to 0. Well, not really, because there's a lot of duplications. A lot of these operators just, duplicate each other. And in fact, there's really only one operator. I mean, we started with d. The first thing we did is not terribly difficult to understand. We just multiplied it by a number. And then we just transported that operator all around to all of these other source fibers. Sorry, just bugging me that these two Ds weren't aligned with each other. Anyway, so it's a bunch of operators. They're acting on the fibers of a certain submersion, not all of the fibers, but 99.9% of them, except for the ones at t is equal to 0. And you might ask, what can you do at t is equal to 0? And the answer is that this family here extends uniquely to a smooth family. Defined on all the fibers of the tangent groupoid. All of these fellows. And what happens at t is equal to 0, you might ask. That's why these things aren't defined. So here's the smooth functions on the source fiber at over some point m comma 0. And here's an operator which we have not yet defined, but I'm claiming the definition is forced on us by continuity. So this should be some operator dm comma 0. Well, we have these maps psi, which are still up there, which identify the source fibers when t is equal to 0 with just copies of A. So what I should write down here is a copy of A, or rather functions on A. And these are the identifications given by psi star. I mean, compose with psi star, that gives a map in the other direction that as I indicated. And what's this map? I mean, what else could it be? I wouldn't be so cocky if it was anything except what we expect it to be, which is you take the operator d, you drop the lower order terms, and you freeze the coefficients at m. Like that. So no rescaling happened, no nothing. We just multiplied by t to the r, and then everything just works out. Sort of nice. It's all packaged into the way the tangent groupoid is defined. It's much more efficient than what we were doing before with all of those rescaling maps and so on. All of that rescaling is built into the definition of the tangent groupoid because we had all of those different versions of coming from linear algebra of an action of Rn on itself by translation. Namely, you can scale the translations by a factor of t. And that's all you have to do to recapture the entire family of operators that we were looking at before. Now, as to these source fibers, let's just take a look at the proof. I want some, in order to check this, I need some uniform way of understanding all of the source fibers. Here's way one of understanding the source fibers, which only works when t is not 0, and which we used to transport d onto all of the fibers. But the trouble with way one is that it becomes kind of singular when t is equal to 0. This definition, it's not clear what you're supposed to do with it when t is equal to 0. Certainly, you just don't want to set t is equal to 0 because then this becomes a constant map. On the other hand, there are these maps which always work. I mean, this is just the formula for psi extended, but here I'm calling it something else. So here's a point in any of the source fibers, whether or not t is equal to 0, and we'll just send it to A, and that's always a diffeomorphism. After all, this object that we're building, this thing that I'm calling T of M, we know what it is as a manifold. It's A times W, and because that's what we started with, the group A acting on W, and by the way, W was M times R. That's all we're doing here. If I want to understand that these operators extend to a smooth family, this is the gauge, the set of coordinates we need to work in, right? We need to see that after I transport all of the dt operators over to A, there's some formula which allows me to smoothly extend them, these guys over here, there's some formula which allows me to smoothly extend them to t is equal to 0. That's what we need to check. And okay, let's just do it. Get back to the groupoid in a moment. So here's A. Which is one way of thinking about a source fiber. And as long, so this is the map theta MT. And as long as t is not 0, there's another way of thinking about the source fiber, which I was calling a diffeomorphism phi of MT. Okay, and what we need to know is what is the composite of these maps. We want to take an operator here. We've already taken an operator here and transferred it to an operator here. That's what we did down here. That's how DMT was defined. And now we have to understand what happens if we further transfer to A. Okay, so you need to do a little bit of algebra. You can take the inverse of one of these diffeomorphisms and apply it to compose it with the other in one of two ways. But also go in this direction. And that'll give you two mutually inverse diffeomorphisms. And what are these things? Well, in this direction, you're just taking TA and adding M to it like that. This formula's pretty easy. And in the other direction, it's kind of fun. So let's pick I don't know, an M prime. Put it here. I want to get an A element from an M prime element. Well, M prime is in the manifold M and not in the group A. But if I have two elements in the manifold M, there's a unique group element which gets from one to the other. In other words, it makes sense to talk about M1 minus M, and now that's a group element. Okay, and I'm just going to divide by T, so 1 over T, M prime minus M. I think I said M1, but I meant M. So these are the two compositions just written down in formulas. And so up here, I'll put what we started with, which was just dt. Maybe I'll write it out as t to the rd. That's this thing on M. Now we've just built isomorphisms to CC infinity of A. Namely, I guess the way I've done it, I just take the first map and I compose with the first map, the one which sends A to T plus M. What happens? Well, you can just do the calculation and you get some differential operator. And what it is A alpha of M plus T. X minus M. So this is a function of X. M is fixed. It's the fixed source point naming the source fiber times, well, there's a factor of T to the R minus the size of alpha, just like we saw before, and then D alpha, dx alpha. So of course, to write down this formula, I'm using some system of coordinates on A. In order to show a formula like this, I'm secretly remembering that A really was just Rn, and for that matter, M really was just Rn, so I could write down a formula like this. And now you do the calculation, sorry, I can't see it. This is the operator that comes out. It's just the very same operator we saw before. This is the operator that formally we would have called, d omega t, where omega is equal to m. Okay, and it's the same calculation as before. And now you see there's no singularity, there's nothing bad happening when t is equal to 0. All of the 1 over t's that you might worry about, for example, in this formula here, are just apparent, give rise to apparent singularities. They're not real singularities. This operator is perfectly well defined when t is equal to 0. And of course, it is this thing here, exactly what I'm talking about. What a magical, everything just works. I think Alain was the first person to, this construction of, deformation to the normal cone, the basic way of taking a manifold, so far our manifold is just Rn, but of taking a manifold and building a groupoid. So far we don't know what a groupoid is, except it's some kind of deviant thing. This way of taking a respectable manifold and building a deviant thing, of course, this is much older than Alain, but the idea of combining that with index theory, with operator theory, I'm sure that's due to Alain. So in that sense, yes, this is his idea. Whether or not he actually did this, well, he doesn't have to do this calculation because he's a smart guy. He can just see the answers.
Excuse me, I had a question. So,
yeah.
So we were initially defining the tangent. So we had a problem at t is equal to 0 on defining the tangent. On trying to avoid the problem at t is equal to 0, we are using operators and we are coming here. This is what it is, more or less.
So we defined a certain space, big T of M. And when we defined it, there was something special about T is equal to 0, but there was nothing, no singularity, nothing that we had to particularly worry about at T is equal to 0 when it came to building the tangent groupoid. It came from the group action of A, Rn,
right.
Rn times R. when t is equal to 0, that action was special in the sense that it was actually the trivial action. When t is
Okay.
not 0, it was a faithful and transitive action. So the nature of the action changed when t was equal to 0, but the overall construction made perfect sense whether or not t was equal to 0 or not, and you could combine all of the t's together and get a single group action, and therefore a single well-defined C infinity tangent groupoid. So the only place where, I don't know, some singularities arise are in the formulas which relate, which are A and M, these two different ways of thinking about source fibers, the A way and the M way. And there's apparently some strange thing that goes wrong. You see it in this formula up here when t is equal to 0. That's okay, that's just the way it is, but that singularity has no bearing on anything else.
Thank you.
What I'm saying is that everything is completely kosher. Kosher is Christmas. We didn't do anything, nothing up our sleeves, no fancy business. And it just works out beautifully like
Thank
this.
you. Thank you.
Yeah.
So, wait, basically, you're saying if we built that TM and using one identification away from 0, we write down t to the other.
Yeah.
With the phi identification.
Mm-hmm.
And then show, okay, if I somehow make this, pull this back using phi, and I get a family operated on TM, which doesn't really look like t, to the idea it looks like something else, but it doesn't really matter. Like when you write t to the RD, you're it's given by what I said.
Yeah, I'm not sure. Maybe I'll just say, yes, you're absolutely right. Yeah, let's, maybe I'll make a few more remarks which may help. Oh yeah, we just finished up over there. No, why did we finish up? There is where we finished up. Let's build two subsets of T of M. The first one, just the bits of T of M where T is not 0, so the M2A, M1 T's where T is not 0. And obviously the complementary closed set. Which is the set of all places where it is 0. So that's, as we've observed before, when T is equal to 0, the two different M's have to be the same. So I could write it a little more economically like that. And of course, the whole of T of M is the union of these two things. Let me finish a little bit. And these identifications that we were looking at a while ago that I was calling little phi, you could put them all together to get an identification big phi, which is a diffeomorphism, in fact, an isomorphism of a groupoid. And what you get here is M times any real number apart from 0. And the formula psi, little psi, that we gave was, or which is also called theta over there, which was valid when t is equal to 0. You could glue together all of those formulas, and then you'll get a picture which looks like this: A times M times, well, 0. That's optional, I guess, but let's stick it in. So big psi sends quadruple like this to just AM0. That's sort of obvious. And big phi sends a quadruple like the ones at the top, and it just drops the A, which is okay, because we know there's a formula for A in terms of M1 and M2 when T is not 0. That's what these maps are. So the whole tangent groupoid is made out of two things which are not exactly the same. Right now, these are diffeomorphisms, actually isomorphisms of groupoids, but when we officially eventually define the tangent groupoid for any manifold, we'll define the tangent groupoid to be the disjoint union of this and this, the two things on the right-hand side, and we'll explain how they fit together into one C-infinity manifold. But by good fortune, in the case of Rn, you can define the C-infinity manifold into which these two things glue together a priori. And so it's just a little simpler. Otherwise, we'd have to explain how you fit them together. We will explain how these things fit together.
There are two, even though in our case, TM the trivial and there's sort of two charts. The one over the 0, 5, and the one away. We find the one family on the away, we find one family on the chart, and we could show that they go together.
Yep. Now let's go back to let me get a little more honest about this algebraical structure, which I was making fun of. You shouldn't make fun of disadvantaged people for sure, but also disadvantaged objects. I shouldn't make fun of them. So I'm sorry for doing. I apologize to Eckhart for making fun of those deviant, deformed groupoids the way I did. So so let's go back and give that algebraic structure a little more credit. And at the same time, explain something about this family. Maybe we'll keep the family there for a moment. So this thing is set. It's a manifold actually, but here it's a big set, and there were two nice maps. They're actually submersions down to M times R, and one of them we called source. That's the one we're favoring today. And the other was called range or target. Somehow I like range. And you can make out of T of M a category in the following way. Well, the objects are just going to be the set of objects. Just going to be this thing, M times R. And then the morphisms from one object to another, let's just say M1, T1, M2, T2. I'm making a category, so these are just prescriptions. A category has to have a bunch of things called objects and a bunch of things called morphisms between any two objects, and then there are some more things to worry about. But anyway, the morphisms is this. It's just the set of all let me write it this way. I want to use different notation. Maybe I'll call it M prime A M T. So they're supposed to go from here. So the source, that's why it's called source, of this fellow should be M1 T1, and the range of this fellow, didn't have room to put it in, should be M2 T2. So in other words, so the source is MT, so MT has to equal M1 T1, and the range is M prime T, so M prime T has to equal M2 T2. So in particular, if you want to get something non-empty, then you need T1 to equal T2, but you can make this definition anyway. And what makes a category is some kind of composition law. Let's see if we can squeeze it in here. If I have a morphism from one object to another, it looks like this. This is a morphism from M1 comma T to M2. comma t. And in category theory, you're supposed to be able to compose that with any morphism which starts at m2 comma t and ends up at somewhere else, m3 comma t. So it has to look like that, and the composition is defined to be the thing I was writing down before, m3. Oops, now I need to get some notation in here. Let's call this a2, this one a1. It's not necessarily the case. In fact, it typically isn't the case that a1 is equal to a2. Anyway, you just add those together, a2 plus a1, m1. And that's legitimate. What you get is a morphism from the source of the first fellow to the range of the second fellow. And then to be a category, this composition law has to be associative. Well, yeah, it's associative. That's because group addition is associative. And there have to be identity morphisms which do nothing when you compose. Well, yeah, if you look at m comma 0 comma m comma t, under this composition law, that's neutral. It behaves like an identity element on the left and on the right. And this category has a bonus property, which is that every morphism is invertible. If you have any morphism, one of these fellows, here it is, an m prime a m t, it has an inverse for this composition law. Namely, you just switch m prime and m, and you change a to minus a, and that's an inverse. So this is a category in which every morphism is actually invertible. That's not part of the law of category theory, but it's true here.
So I had a question. Excuse me.
Yes.
So you are here fixing m, so this is the tangent group. This is a groupoid, right?
Yeah.
So this is the tangent groupoid that we are constructing. So
yeah, we are constructing and discussing the tangent groupoid for
right,
m,
so
in the particular case where m is equal to the Rn.
So, okay. How in this, so this is the general category, and once we fix Rn corresponding to Rn, we get the tangent groupoid that we're looking for.
Yes.
Thank you. Thank you.
And we'll figure out how to do this for general manifold, hopefully by the end of the lecture.
Right. So is this a stack?
Is this a stack? Stack is something like a Morita equivalence class of groupoids, something like that.
Okay,
basically in the world, could basically be in the world of stacks, but that's
right.
That's not the direction we're going. Yeah.
Thank you.
Yeah, sorry, keep looking in the wrong thing. Oh, there's a camera there too. Oh yeah, you're right. Okay. I guess they anticipated this problem and solved it. All right, good. The reason I'm telling you all of this is only to discuss a very minor detail. I mean, right now, only to discuss a very minor detail. We'll use this structure in a more serious way later.
Excuse me, I just wanted to ask you one. Is it an analytic object?
Yes. Well, C infinity object. This exists, although I didn't mention it.
Right.
This is a Lie groupoid. Everything is C, all of the maps that we're discussing here are in the appropriate sense C infinity maps. So it's analytic in that sense.
Thank you. Thank you.
Yeah, as you can see from the formulas are just, it's like algebra. It's even, it's the only reason we're limited to C infinity in general is that manifolds just live in the C infinity world in general. Yeah. Yep, and if you took an algebraic variety, then this would be an algebraic. Well, if you took a non-singular algebraic variety, that's what this thing would be, and so on and so forth. Well, that's a bold statement that it always works all the time, but it works in those cases, yeah. All right. Let's go back now to functions. That's our obsession. suppose we look at two different source fibers corresponding to two objects in this category, for which there is a morphism between them. Okay, so what do I want to do? These are all of the morphisms which begin at M2T. So I'm doing a little bit of messing around here, and these are all of the morphisms which begin at M1T. And I want to imagine that if I have a function on here, I can, on this space related to M1T, I can obtain a function over here. So I need to take that obtained function and evaluate on a morphism which starts here. And I have to define it in terms of a function which is already defined on the M1 things. So I probably need a morphism like this. Which is another way of saying a triple, which looks like, well, I've got the notation from according to my conventions the wrong way around, but that's how we write morphisms which whose source is M2 and whose range is M1. Anyway, if you take such a morphism and you want to evaluate it on something in here, let's call it, if we have a function which lies in this space, and I want to get a function over here, then the idea is I just compose with eta like this. So I screwed it up. That seems maybe to me, and I screwed it up in a good way. So eta and gamma have to be composable, and gamma has to begin at M2, so eta has to end at M2. So it should look like this. It's just what I want. So that's a morphism from M1 to M2. Perfect. The rest is just my Scratch working. Get rid of it. Composition gives a map from morphisms which start at one place to morphisms which start at another place. This is what right composition does. And all of these composition maps between source fibers are diffeomorphisms because all of the morphisms in this category are invertible, which I didn't write down, but I did say it. So here we're using this fact, all morphisms are invertible. And what it means is that if you take this groupoid structure into account, it makes sense to talk about equivariant families of operators. What are they? Well, they're operators which satisfy which give rise to the obvious commuting diagrams, which I shall attempt to write. So here's the operator D, M1T, mapping between functions from acting on functions on the source fiber for M1T, which is that. Here, after a certain amount of agony, here we've defined a map from functions on one source fiber to functions on another source fiber. Hopefully I got it right. And on that, acting on functions on that other source fiber, there's another operator, dm2t. And using composition by the same morphism to get both vertical maps, you can construct little squares like this, and a family of operators, whether or not they're differential operators, will be called equivariant if all of these squares commute. And the fact is that the smooth family in the lemma over there is equivariant. that's an economical way of saying two things. First of all, when t is not 0, all of these operators that we built are all basically the same. For a given fixed value of t, all of the operators that we built are all basically the same, because for a given fixed t, as long as t is not 0, and any m1 and any m2, there's a unique morphism from m1t to m2t, which transports the operator on one fiber to the operator on the other fiber. So they're all canonically identifiable with one another. That's what it means for a family to be equivariant away from t is equal to 0. What it means for a family to be equivariant when t is equal to 0 is much more interesting, because when t is equal to 0, I don't know if it's written on the board anywhere, when t is equal to 0, all of the morphisms go from a given object m comma 0 to itself m comma 0. That's how the composition works. So in the picture that I've drawn here, this little commuting square, when t is equal to 0, it's a much more constraining condition, because the operator upstairs is going to be the same as the operator downstairs, the d operator. So an operator's family of operators is going to be equivariant only if, when t is equal to 0, the operators d, m comma 0 satisfy some intertwining conditions. And then now you need to ask, what are these morphisms here, these vertical morphisms? They're just translation maps after you identify the source fibers at t is equal to 0 with a, as we were doing via the famous maps psi, aka theta. Okay, so for an operator, family of operators to be equivariant, in particular, the operators defined over t equals 0 have to be translation invariant. So that's kind of nice. When we say an equivariant family of operators, maybe smooth equivariant family of operators on the source fiber, on the one hand, we're saying there's really only away from 0, there's just a one parameter family of operators, d sub t, like we have here. And the other thing we're saying is that when t is equal to 0, all of the operators have to be translation invariant, like they were in the theory of scalable operators, and in particular, like they are in the theory of differential operators. All of the families that we'll be considering are translation invariant families. Let me, because I think I mentioned it, there are two things I want to talk about, and I have time just for one. So I'm going to skip over the notorious zoom action, the rescaling action, which means I can't quite get as far as talking about scalable operators today, because I do also want to talk about diffeomorphisms and the strange effect that diffeomorphisms have on the space Tm. So that's the end of that. Let's go to an entire fresh new board to begin this thrilling story. And the correct way of discussing this business of diffeomorphisms is to study diffeomorphisms which are locally defined on Rn. But just to get us started, I'll consider the global story. So suppose I have a diffeomorphism of Rn. Diffeomorphism. Eventually, next time, we'll want to talk about a diffeomorphism from one open subset of Rn to another, but this is just a bit easier to talk about this thing here. Let me build something which is just a function, I guess, to begin with, and then we'll improve that statement. Let me build a certain function in the following way. It's kind of amazing that this works. Remember, T of M is built apparently using the full structure of M as a vector space, namely addition and scalar multiplication. We all threw it into a big bag. It was necessary to have both addition and scalar multiplication before we could define what the tangent groupoid is. Now I'm saying, well, suppose you have a diffeomorphism, just a diffeomorphism, you know, not compatible with scalar multiplication, and nor also should it necessarily be compatible with addition, just something. Those two conditions aren't completely independent. Anyway, just a diffeomorphism. Well, we had a map that we called psi, and we had a map that we called phi, which identified a certain respectively closed subset of T of M with A times M, and a certain open subset with M times R times 0 I wrote before. Decided not to do that now. Times R cross. Remember that? The tangent groupoid has two personalities. There's the T equals 0 personality and the T not 0 personality parts. And I'm trying to build a map here, F star, out of the diffeomorphism. And I'll just build it so that the following diagram commutes. What I'm going to write down over here are two diffeomorphisms, and in particular, bijection from this thing to itself. So for sure, there's a diffeomorphism, not a diffeomorphism, a set theoretic bijection that I can build over there. So what shall I do? Well, if I have a triple, like I have over here, M2, M1, T, I'll just apply F. That's a formula, and it's a diffeomorphism. What about if I have a pair consisting of a vector and a point? Well, what I'll do is I'll take the derivative of F at the point M, and I'll apply it to A. df, maybe I don't need brackets there. It looks a little over the top, doesn't it? Better maybe at the point M of A. So it's all grammatical, at least. A is a vector and the derivative is a matrix, a linear operator. So you can apply the derivative to the vector and then you get another vector. And well, it's not quite grammatical because the punctuation is off. So the first thing in this pair is a vector in A, and the second thing is the point M. F of M, excuse me. That wouldn't sort of be, wouldn't be right, would it, just to have M? There. And this thing is a bijection. Each of the pieces separately is a diffeomorphism. And the wonderful fact, which we'll end with, is just a calculation. It's Taylor's theorem, which we've actually encountered before. So the first interesting thing, maybe I'll state that as theorem 1. This is just a fact. Even though we built T of M using scalar multiplication and addition, this F star is actually a functor. It respects the algebraical structure that we're talking about here. It stirs around the objects. Obviously, I should say, if I'm talking about functors, how it acts on objects, but it acts in the obvious way on objects by just application of F. And it acts on morphisms, well, in the way that's given by this picture. And it's a functor. It's compatible with, if you like, source and range maps, and it's compatible with composition. And it's an isomorphism of the category to itself. It's a functor, which if you start off with the inverse diffeomorphism, you'll get another functor, and it completely undoes, obviously, the functor you started with by the chain rule. So algebraically, everything is in great shape. And it's a little surprising given how much group theory and linear algebra was involved in the definition. But actually, that was a bit of a red herring. This thing exists. It's coordinate independent in the sense of this picture. And then the second thing, part of the theorem, the second part of the theorem, the second theorem, is that F star is a diffeomorphism. So it's an automorphism, not just of groupoids, not just functorial, it's an automorphism of Lie groupoids with this extra C infinity structure. And that means taking the two different parts of this formula and just reconciling them. We have 5 minutes, maybe enough to do a little scratch calculation. This is almost evident from the formulas that are written here. Why is this algebraically speaking a functor? Well, you can transport the groupoid structure on Tm separately to this part of the groupoid away from t is equal to 0 and to this part where t is equal to 0. And what you see is that the groupoid structure basically just corresponds to addition in the coordinate A over here, and it corresponds to this concatenation matrix multiplication operation that I was describing before over on the right, and the formulas clearly are sympathetic with those algebraic structures. So the key thing is this, and what's happening is the following. If you take an M, A, M, 0, and you do the math on this, then what you're actually getting here is f of m, derivative of f at the point m applied to A, f of m 0. And of course, you have away from 0. This is a little bit interesting. Away from 0, we're defining the map by initially forgetting about the A coordinate. The A coordinate is forgotten. The top map, big phi, is the map of forgetting A. And so you have to solve for A to figure out what the formula for F star is as it acts on the tangent groupoid. What does it do to M2? Well, it has to do that. And what it does to M1 is you just apply F. And what it does to T is nothing at all. And now you have to solve for A. You have to find the A with the property that T times A plus f of M1 is f of M2, because that's what an element of the tangent groupoid looks like. So what you have to put here is f of M2 minus f of M1 over T. But as T goes to 0, I mean, this is the derivative, right? So it's sort of interesting. Let's just, we have 1 more minute now. Let's just pursue this one more line. In order to understand what's going on properly, we should focus on this systematic picture that we have of T of M, where we drop the M1 term, and then the rest is just what's written here. So now, here's the map F star. Now we can sort of see what's going on here. The interesting thing is what happens. I mean, we already have the picture when A is equal to 0, when T is equal to 0, but what about one of these triples? To write down the formula for the map, now I have to figure out the M2 in terms of the M, but the M2 is M plus TA. So what this thing is F applied to M plus TA minus F of M divided by t. That's the a coordinate, f of m t.
Sir, excuse me. So we had already proved before that T tangent space of M is isomorphic to A cross M cross R. We know that the right hand side is an isomorphism. That's using that we want to prove that F star is also isomorphism.
I want to prove that f star is a diffeomorphism, that it's a smooth
Right. F
map.
star is a diffeomorphism.
And I'm trying to show that it's a smooth map by writing down a formula for it. This is what happens when t is not 0, and when t is 0, am 0. As we saw this, let me just write it again. This is the derivative of f at the point m applied to a, comma f of m, comma 0.
Thank you. Thank you.
And now we're in business, right? Because if you look at this fellow, you can write this as t by Taylor's theorem with remainder or something. This is t times g of a function m comma a. T. With the property that g of m a 0 is the derivative. So calculus tells you that there is some function g. With this property, if you have a smooth function, and if it vanishes when t is equal to 0, it's t times another smooth function. And moreover, that other smooth function has the property that when you plug in t is equal to 0, you get the derivative, which is exactly what I wrote down. So now if you write down the formula for this map in terms of g, the singularity, whatever, the dividing by 0 problem that appears to exist here goes away. This map is expressible everywhere as in terms of g in a completely smooth way. So that proves that f star is smooth. And why is it a diffeomorphism? Well, you can do exactly the same thing with the inverse of f and get the inverse map. So it's sort of a surprise, really, that something built completely out of linear algebra turns out not to depend on linear algebra at all. Or maybe it says that calculus is just linear algebra anyway, or something. All right, good. So what we'll do next time, and now it's a breeze, is define scalable operators, redefine scalable operators using the tangent groupoid. And we'll see immediately, thanks to this calculation, that scalable operators are invariant under diffeomorphisms, global diffeomorphisms at the moment, but by a small variation on this argument, also in some local, suitable, more practical sense, they're invariant under local diffeomorphisms if they're supported in just little open sets. And then we can patch together, we can talk about scalable operators on a manifold. If, in the olden days, that's what you would do. You would just patch together, but now, of course, everyone wants globally defined, invariantly defined objects, and so we'll also define the tangent groupoid invariantly, the scalable operators invariantly, et cetera, et cetera. Good. Thank you very much. See you.
Thank you.
Next week. Thank you.